Hello. Yeah, please be sure and put your name in the chat. I've been having some major issues with computers and Zoom and cameras. Right now, you see the wonderful picture. That is what is showing with the camera in the classroom. The camera's on. It was working fine. And then all of a sudden, the computer decided, I don't like it. Or Zoom has decided it doesn't like it. So what I have to use now is this camera. And here, let me do something real quick. So I changed my name so you can see the more of the screen. And so, yeah. So, hi.
Oh, sorry, sir. It just,
Okay.
I'm gonna, good morning, like.
Okay. So I'm trying to remember where we left off. Did we do graphing polynomials and finding rational zeros? I mean, finding the zeros and all that stuff?
I think we left on the objectives, so I'm not pretty sure about it.
We left off on the intermediate value theorem.
Okay. So let me find that. There it is. There we go. Yeah. This is less than ideal. And let me see if this is make that glare better. No. But when you pin my screen, you can kind of see through the glare a little bit. And if the glare, you can't read what's through the glare, let me know and I will deal with it. Right now, yeah, the glare is just barely hinging on this right here. So, you can still read all this. Intermediate value theorem is a very powerful and important theorem. We use this in conjunction with other theorems to prove things and show things in calculus. And basically what it says, if you have two values that are one smaller than the other one, and we typically use A and B for this, where A is smaller than B, and f of A and f of B have opposite signs. So f of A is negative and f of B is positive, or f of A is positive and f of B is negative. That means we're going to have to cross the x-axis somewhere. If the function is smooth and continuous, we're going to have to cross this x-axis somewhere. Right? So it's a polynomial function, which means it's going to happen. And all that really needs to be true is that the function is smooth and continuous. It doesn't have to be a polynomial function, it just has to be smooth and continuous. So when it's smooth and continuous, it doesn't even have to be smooth, it has to be continuous. It will cross the x-axis somewhere between eight. That is somewhat intuitive, but in mathematics, even if it's intuitive, we need to have it or a theorem that states it or proves it. So that's what the intermediate value theorem states. So if you know oh, I didn't have to put that button. Yeah, you can read that, can't you? Yeah, the camera in here, which is over there, the computer isn't recognizing that the camera is there, or Zoom is telling me that the Zoom screen, that the camera is sending a black. Here, I'll show you. There, I put it on that camera, and
Actually, it seems kind of blurry, sir, and the connection is pretty unstable.
yeah. So yeah, the black screen you see there is what Zoom thinks the camera is doing. But for some reason, it doesn't have a problem with my camera. Oh, you know what? No. I could find out which USB port goes to the camera and put that in one of these ports down here. And that would work. Okay, but anyway, that function there is f of x equals 2x to the fourth plus, is that just x squared, I think, minus 1. So we want to show that it has a real zero between those two numbers. So we want to find out, is f of 0 positive or negative, and find out if f of 1 is positive or negative, and are they opposites? So doing f of 0 is trivial. It's just -1, right? Because these two go to 0. And then f of 1 is 2 times 1 to the fourth plus 1 squared minus 1, which is 2 times 1 plus 1 minus 1, which is 2. Is that right? It shouldn't be right. Oh, that's right. So there's a sign change. Yeah, it's going to be a little out of focus because that camera. So we evaluate it at, so it is 1 and -1, -1 and 2. So there is a sign change. So it follows that there is a 0 between 0 and 1. So they're going to ask for the 0. Right, so we want to find two consecutive integers, a and a plus 1, for which f has a real 0 between them. So we can approximate the real 0. Yeah, the word 0's kind of got left off in the picture. If I rotate it, wait a little bit. That's better. But now you're getting a glare right here. All right, this is subintervals. So you want to find where you have two integers that are consecutive, where there is a sign change. So, and then between those two, you divide it into 10 subintervals and evaluate f at each endpoint of the subinterval until the sign of f changes. And then by the intermediate value theorem, there is a real 0 in there. And then you have a new interval that you can divide into 10 equal subintervals. And then you just start checking the endpoints of each subinterval until you get a sign change. And then you know there's a 0 in there, and then you can do it again. Divide it into 10 equal subintervals until you reach the appropriate accuracy. Okay. Oh yeah, please put your name in the chat and pin my screen. Now, find the not the positive real 0, but a positive real 0 of f of x equals, so it's the same function they gave us before. Okay. So now the question is between 1 and 0. Because f of 0 is -1 and f of 1, what is f of 1? Oh, 1 gives us 2. So between 0 and 1, we have a 0. We already determined that earlier. So between 0 and 1, I'm going to have 0.1, 2. So this is 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, and 1.0. Now I have my 10 intervals. This is 0.0. And technically, I'm supposed to put a 0 before that decimal. So we look at 0.1. Does that give us a 0? Does that give it? We know that f of 0 is less than 0. So we want to find out, is f of 0.1 greater than 0? If it isn't, then I go on to f of 2.2. Is that greater than 0? And then I do f of 3, and f of 0.3, and f of until I get to a place where it's greater than 0. Then between those two consecutive endpoints, I have a 0. And so I'm going to put 0.1 in for x. And so 0.1 to the 4th power, 0.1 to the fourth power equals 0.0001. How do you know, Mr. Reed? Because I do. And then I'm gonna, what is that, a 2? So I'm gonna multiply that by 2. So I have 2.00, no, I have 0.0002. And then I'm gonna add 0.1 squared, which is 0.01. So now we're going to have a 0.1 to it. So 0.102. And then we're going to subtract 1 minus 1. Well, that's going to be 0.0102 minus 1. So 1 minus that, that's going to be 0.980. Negative. So 0.1 at 0.1, F is still negative. So at 0.2, so I put 0.2 in. 0.2 to the fourth power. 2 times 2 times 2 times 2. 2 times 2 times 2 times 2 is 16. So 2.2 to the fourth power is 0.0016. And then we're going to multiply this by 2. And that's going to be 0.0032. And we're going to multiply that by 0.2 squared, which is 0.04. So we're going to add that 0.04. So we get 0.0432. And we're going to subtract 1 from that. Well, that's still going to be negative. So 0.2 gives us a negative number. So now we put 0.3 in. And I'm going to let them do it. And here they wrote all the intervals. I did it on a number line because I think number lines are easier to work from. That's me. So here's 0.1, that's this endpoint. 0.2 is this endpoint. 0.3 is this one. 0.4. So yeah, so I think it's easier to visualize the intervals this way than it is writing those intervals that way. Please notice they include the endpoints because the endpoints could be, one of the endpoints could be a 0. So at 0.1 it's negative, 0.2 it's negative, but does not exceed. Now they're moving up. They're getting closer to 0. At 0.4, and then 0.5, well, it's getting way closer to 0 now. And 0.6, 0.7. So between 0.7 and 0.8, we had a sign change. So that means there's a 0. There's a 0 in here. In here, there's a 0. So now we go from 0.7 up to 0.8, and we divide that into 10 intervals. 1, 2, 3, 4, 5, 6, 7, 8. So we have 0.70, 0.71, 0.72, 0.73, 0.74, 0.75, 0.76, 0.77, 0.78, 0.79, 0.80. So now we check all these endpoints until we find another change in 0. Now we know it's going to be negative here, right? So now I need to check the next one. Is it going to be negative or positive? Is this one going to be negative or positive or zero? Realizing that one of those could be the zero. That happens every now and then. And so they do it again. And so 0.01, oh, between 0.01 and 0.71, between 0.70 and 0.71, we have another zero in here, so we don't have to go that far. So now I'm going to subdivide that. So we're going to go from 0.710, 0.711, 0.712, 0.713, 0.714, 0.715, 0.716, 0.718, I mean 0.717, 0.718, and 0.719 until we get to 0.720. Okay, so I'm going to check all those endpoints. But to choose zero, well, I would have to check, I would check here to see is my sign change below 0.715 or above 0.7? Oh no, that's a zero here, right? Uh-oh, I went 700, 701, 70. So those, all those ones in there need to be zeros. Sorry. I went on the other side. Because we're supposed to go up to 7.1, I mean 0.71. Okay. So I would check to see when it changes sign, because then it's going to be either closer to 0.70 or 7.1. I would go another level. If I was just looking at one decimal place, then 0.7 would work because it happened before 0.75, the sign change. Okay. Graphing polynomial functions. So we're looking at the zeros here. What are the zeros of the function? That tells us where it's going to cross the x-axis. And then find the y-intercept. That tells us where it's going to cross the y-axis. And then we look at end behaviors. Okay, so you determine the end behaviors. Well, that's the first thing I ask. On the test, you will have a question about graphing. And so f of x equals 3x plus 1 times x minus 2. It's going to be x to the third power. Because we're going to end up. We're going to end up adding these exponents here on the two binomials. So they add up to a 3, so it's a third degree polynomial, which means we're going to have end behaviors are going over here. End behaviors are going in opposite directions, either down to the left and up to the right, or up to the left and down to the right. Since my leading coefficient is going to be positive, because 3x times x squared gives us 3x to the third. So my end behaviors will be down to the left and up to the right. Or as x goes to negative infinity, f of x goes to negative infinity, and as x goes to positive infinity, y goes to positive. So I'm saying the same thing with those two arrows. All right. So what they do is they expand the polynomial and they get this nice little thing here. And this 3x to the third tells us what's happening here. The +4 here is the y-intercept. Setting each of these equal to 0 gives us the x-intercept. Realizing that this one has a multiplicity of 2, which means it only touches at x equal to 2. Where here it's going to pass through x equal to a negative 1/3. Because it has an odd multiplicity. That has a multiplicity of 1, which is odd. Oh, they expanded it and then they combined the like terms. The negative 12x squared and the x squared, and then the 12x squared and the minus 4x, 12x and the minus 4x. Make sure you do your multiplying correctly. All right. What they did here was 3x times x squared, 3x times a minus 4x, and 3x times 4, and then 1 times x. So that's how they got these. And then 1 times x squared, 1 times a minus 4x, and 1 times 4. That's how they got these. And then they combined like terms. And that's how they got that down here. Here they squared this by doing x minus 2 times x minus 2 to get this thing. Or if you know the shortcut for squaring a binomial, it's the first term squared, multiply the 2 together and double it, and then square the last term. Yeah. Polynomial is degree 3. The graph resembles the graph of 3x squared for large values of x. Which is, so that means that this. Okay. Find the x and y intercepts. The x-intercepts is setting each of these equal to 0. The y-intercept is looking at this here and saying that it's this number. Because the constant is, for a polynomial function, the constant is where it crosses the y-axis. I keep forgetting that freaking camera is not working. Or it's working, it's just computer doesn't recognize. Or I'm not too sure what's going on. I think it recognizes it, it just doesn't know what it is. What it's saying to it, so it shows a black screen. Okay. So putting 0 in for x, you get 4, so that's the y-intercept. Setting each of the factors equal to 0 gives us x equals 1/3, negative 1/3, or 2. So right now I have 3 points I can graph. I have 3 points I can graph. I can graph 4 on the y-axis. I can graph a negative 1/3 on the y-axis, on the x-axis, and a positive 2 on the x-axis. All right. I know because of the end behaviors, which is still right here, down to the left, that means this is the leftmost x-intercept, so that means it's going to go down from here. The multiplicity here is 1, so it's going to pass through. And this is the furthest to the right of the x-intercept, so that means it's going to go up from there. And because it has even multiplicity, that means it just touches, it bounces back up. And so what's left to find? I want to find out what happens at -1. I want to know what happens at 1, and I want to know what happens at 2. So I can sketch this graph out. Now, I could probably go up to 3 and 4, or -2 and -3, or something like that. But those numbers are going to be sufficient. So that tells us so the graph crosses, and at 2 it touches. So I've already discussed that here. So we graph those points. So it's going to have at most 2 turning points. Well, this shows me that it's going to go up, and it's going to have to come back down, and it's going to go up again. So yeah, we have 2 turning points. So well, we need to find more points, because I don't know. I know there's going to be the turning local maximum here at this turning point, but where is it? So if I put 1 in for x, let's see, that's going to be 3x plus 1 times what? X minus 2 squared. Putting 1 in for x, we get 4 here. We get 1 minus 2, which is -1. -1 squared is 1. So at f of 1 equals 4. So it goes through 4 here. So that means it's going to come up to the y-intercept, go up, and then the what do you call it? The local max there is going to be between 0 and 1. And then I'm going to put 2 in for x. So that's going to be 6 plus 1, which is 7. And then oh, that's a 3. That's supposed to be a 3 here. So 3 times x times, because this is 2. That's going to be 9 plus 1, which is 10, times 3 minus 2, which is 1, and 1 squared is 1. And so that's just 10. So it's going to go all the way up to 10 up here somewhere. And so boom, shoots up that way. And then putting -1 in here, -1, so that gives me a -3 plus 1 is a -2. And -1 plus minus 2 is a -3. -3 squared is 9. So that gives me a -18, which is way down here somewhere. And so it's going to plummet down pretty fast. So there I have it. Their graph is going to look a lot prettier than mine, but it's basically going to be the same thing. I don't even think they're going to find this. I think they plugged in and found what the x value for this point is, the x and y value for the local maximum. Find additional points on each side of any x-intercept, and that's what I did. That's what I always do, and that's what I tell people to do. Find points on either side of the x-intercepts, other than the y-intercept. Okay, so the y-intercept is between these two x-intercepts, but I mean another point. And so I always do that. Yeah, their scale is way different than mine, so that's why it looks way different than mine does. Their y is kind of compressed down, where I did not have such a compressed y scale. My scale for y is not that compressed. And so I found, -1, -18, I found that one. And 3, 10, and 1, 4. They just made the scale fit the points that they found. That's all. And you can do that too. You can make your scale fit. Okay, the scale in the X direction does not need to be the same as the scale in the Y direction. So each point here is in the X direction is 1 unit apart, where each point here in the X direction is 5 units apart. Oh, keep forgetting that it's over here. Because that sucker isn't working. Oh yeah, you can't see it because the glare is real bad there. Here, let me look. So, here we go. Now the glare is just over here. And so, yeah, this is showing 3 to 10. So if I cover up that glare, it'll show up better. Nope. Okay. Anyway, that's a 10. Has parentheses here as well. And I hit the blackout button. Blank screen, whatever. Okay. So we evaluate at -1, 1, and 3. Help establish the scale in the y-axis. So we found f of -1 was -18, f of 1 was 4, f of 3 was 10. So we chose a scale to go from -20 to +20. So these 2 points will be within that range. And also this point, since this point is between these two in the y direction, it's in between as well as the x direction. So then we plot those points and draw a smooth continuous curve that connects them all appropriately. And this is what you're going to be asked to do on a test. Only they won't be nicely factored like these are. Okay. They're not going to be nicely factored like these are nicely factored. So here my x, well, this is a 4th degree polynomial. Do they multiply it all out? Yeah, they multiply it all out. Okay. So they multiplied the x plus 4 times the x minus 4. And then they squared x plus 3. And then they multiplied the 2 together. Now, you can do the arrow method there, or you could do what I do to multiply these 2 quadratics together. And that's using a form of vertical multiplying. Okay, so I start with the +9, I multiply each one of these by +9. So that gives me 9x squared minus 3x minus 27x minus 36. So I'm done multiplying by the +9. Now I move on to the 6x. And I start by multiplying the last term, the constant, then the middle term, and then this term. And I write them underneath the appropriate. So I create columns of like terms. So 6x times a minus 4 is a minus 24x. And I write it under the minus 27x. 6x times 3x is a minus 18x squared, which I wrote under the x squared. And 6x times x squared is 6x to the 3rd. So that comes out here in front. And there's not another x to the 3rd, so it's all lonesome after. But that won't be for long. And now I'm done multiplying by the 6x, and I move on to multiply by the x squared. X squared times a minus 4 is a minus 4x squared. Here's x squared column, so it's a minus 4x squared underneath there. Now, x squared times a minus 3x. X squared times x is x cubed. So this becomes a minus 3x cubed, which goes underneath the x cubed, the 6x cubed, so minus 3x. And the last multiply is x squared times x squared, which is x to the 4th power. And now I wrote this so that my like terms are in nice columns. There's only one constant. They're both minus, so I add the numbers and keep the minus sign. So that's going to be what? 51? 51x squared, 51x, right? 51x, a minus 36, a minus 51x. This should combine to a minus 13x. So negative 18 and negative 4 is a negative 22x squared, and I'm going to combine that with a positive 9x squared, which gives me a negative 13x squared, minus 13x squared, which is what? Same thing here. 6 minus 3 is 3, so that's plus 3x to the 3rd, which is the same as that there, and then x to the 4th, because there's no other x to the 4th. I like this method because it feeds my OCD. It's nice and organized, and everything works out nicely. Putting like terms in columns rather than when doing this method, everything's all spread out and you have to hunt and peg for like terms. I like this because you end up putting like terms in columns. If you do the arrow method, you can still write like terms in columns. But you also have to be aware that you want it in descending order. Why? Because that's how we write them. Not that it's any more correct than the other way, but that's how we write it. I have some friends, math instructors that say you have to write it this way. I don't. But writing it this way is less confusing than having it like having the minus 51x in front of everything. So. All right, our y-intercept is negative 36. So we have the point 0, negative 36. And our x-intercepts are negative 1, 0, negative 3, 0, and 4, 0. Negative 3, 0 has a multiplicity of 2. Multiplicity 2. So that means it's going to touch at negative 3, where it's going to cross at negative 1 and positive 4. Okay. The end behaviors are both going up because it's an even function. That means both end behaviors are both going up or both going down. Because the coefficient here is positive, that means they're both going up. So end behaviors are telling us it's going this. And so far right now, I can do this much graphic. I know it goes through 1, negative 36, so that's way down. Negative 36. And at negative 1, it's a 0. And at negative 3, go down a little further from negative 3. Negative 3, it's a 0. And at 4, it's a 0. All right. So this is the most negative intercept, x-intercept, so it's gonna go up from here. And it's also gonna go up from this one. And so that means it's gonna come, and since this has a multiplicity of 2 at -3, that means it's gonna bounce off and come up, and then it's gonna come through -1, and then it's gonna come back up through over here, because the multiplicities of these two are 1, which is even, which is an odd multiplicity, which means it passes through. Now we have to find other points, okay? I can come down here to -4. I can come up here to +5. I want to find out what happens at -2. I also want to find out what happens, let me see. If I find out at 2 and possibly 1, I want to see what happens there. Where is my local minimum going to be down here? Right? It's a 4th degree polynomial, so that means we'll have at most 3 terms. Well, here's 1 term. There has to be a term here, so that's 2. And there has to be another term here, so that's 3. So we have 3 terms. We have the maximum number of terms we could possibly have. So, yeah, we already talked about that. The y-intercept, the x-intercepts are setting it equal to 0. So yeah, so -1, -3, and +4. The real zeros, yeah, same numbers. Zeros 1 and 4 have multiplicity of 1, so the graph passes through. And -3 has a multiplicity of 2, so it just touches. And what's that say up there? See it? So the number of turning points, n-1, which is 4 minus 1, which is 3. And from what we've sketched out about the graph so far, it does have those 3 turning points. And so they were doing the same thing. They want to look at what happens at -4, at -2, and oh, they did 1 and 3. I would have done 1 and 2. But because I know at 3 it's going to be closer to 0 than it is at 2. So I would have done 2 instead of 3. So I'm trying to remember what the function was. Second, I need to rewrite this. And so I have x plus 1 times x plus 3 squared times x minus 4. And so I use that version of the function and not this version of the function to graph by. Because I can by putting numbers in, like putting -4 in for x here, I can find these numbers in here relatively quickly and just multiply them together, which is an easy thing to do. So yeah, okay. So putting -4 in for x, we have -4 plus 1, which is a -3. -4 plus 3 is a -1 squared. And then -4 minus 4 is a -8. So this is just a -3 times a -8, which is 24. So f of -4 is positive 24. Well, yeah, we knew it was going to be positive. So if that's 36, then this is about 24. So it comes up to here. Lines up better. So I know at this end, it's going to go like that. And then putting -2 in, -2 plus 1, -2 plus 1 is a -1. -2 plus 3 is 1, so that's 1 squared. And -2 minus 4 is a -6. So that's -1 times 1 times -6, which is +7. And +7. See if this is 8, that is 16, and then 24. And so that's going to be about here. So it's going to come down and then kind of flatten out and then come up and then dive right back down again. So this is the local maximum is going to be awfully close to negative x equal to -2. And then putting 1 in for x, we have 1 plus 1, which is 2. 1 plus 3, which is 4 squared, which is 16. So 2 times 16 is 32. Times 1 minus 4, right? 1 minus 4 is a -3 times a -3. So that gives me a -96. Oh, way down here, -96. Well, you can't see it. The camera isn't pointed that far down. So I would have to scrunch these down even more. And then putting 3 in, 3 plus 1 is 4. 3 plus 3 is 9. I mean, 3 plus 3 is 6. So that's 4 times 36. And 3 minus 4 is a -1. So that's just going to make this negative. And so that's going to be 144. So a -144 at -1. No, at -3. Let's see what they did, because their graph is going to look a lot nicer than mine. And for a test, I make sure that the numbers are going to be smaller or easier to deal with. And so, yeah, so they got the same numbers I did. And so they make the chart appropriately. So, yeah, I would have done 2. 2 is going to come down a little bit further than 3 is. Right? 2 plus 1 is 3. 2 plus 2 is 4, and 4 squared is 16. So that's going to be 48. And so that's going to be a -2 times 48. Oh, what did I do wrong? 2 plus 1 is 3. Oh, that's a 5. And 5 squared is 25. So that's going to be 75 times a -2, which is a -150. So 2 is going to be about here. Yeah, it moves pretty severe upwards. And then you have this tiny little bit of a dog leg in the middle on its way down. And then it flies upward. I would find out what it was at 5 just to see what's happening. So 5 plus 1 is 6. And then 5 plus 3 is 8. 8 times 8 squared is 64. And 8 minus 4 is 4. So 4 times 64 is 256 times 6. Wow. So that's going to be 1,536. So at 5, it really explodes. hugely. It explodes upwards very, 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 very fast. So I think if you put -5 in there, you'll see that it grows almost as fast. Okay. Properties of rational functions. First thing we're gonna do is find out what rational functions are. Okay. And then we're gonna discuss the domain of rational functions. The range of rational functions can be all real numbers or a limited portion of the rational is either something above going from some number to positive infinity or negative infinity up to some number. But there won't be a gap. It'll be one of those three. No, I just realized I could use the microphone. My little thing here has a microphone. Okay. Okay. And then we're going to find vertical asymptotes and find horizontal and oblique asymptotes of a rational function. And they don't talk about graphing here, but I do graph it. Because I don't see the point about talking about these things without looking at the graphs. And so I do this, find the graph. Finding the vertical asymptotes and the horizontal asymptotes gives you a framework, scaffolding on which to hang the graph. And we'll look at that, what's happening for that. First of all, what is a rational function? A rational function is in this form where the numerator and the denominator are rational, are polynomial functions. And the Q function is not the zero polynomial. What they mean by the zero polynomial is that y equals 0. So you don't get that y equals 0 in the denominator. But the function does not exist when the denominator is 0. So whenever q of x equals 0, that equation equals 0, you have to eliminate those x values from the real number or the domain. And usually they say over here where q of x does not equal 0. Which kind of eliminates the zero polynomial as well as x values that make that polynomial 0. So basically, a rational function is a fraction where the numerator and denominator are polynomials. Realizing constants are a polynomial. The domain of R is the set of R. Okay, we already discussed that. So the domain here is where x plus 2 is not 0. X plus 2 is not 0 when x is not -2. -2 makes x plus 2 equal to 0. So I want to eliminate x. I want to eliminate -2. from being put in there. So I say x minus x equal to negative, x cannot equal -2. It's all real numbers such that x is not negative. So it's any other real number other than x minus x other than -2. Right? We're always going to be factoring. Okay, we're always going to be factoring from this point on. So we're factoring. And this is later. Okay. So the word here is the, you can kind of see it. So the domain is a set of all real numbers such that x is not -5 and x is not 5. So we always want to factor things. Here's the difference of two squares. So factoring the difference of two perfect squares is the sum and difference of the two square roots. Square root of x squared is x, square root of 25 is 5. So it's x minus 5 and x plus 5. And you set each of those equal to 0, and that tells you that -5 and 5 cannot be in the domain because they make the denominator 0. Right, this one. They say it's a set of all real numbers. Well, let's take a look at x squared plus 1 equal to 0. Is there any number I can put in for x that will make it a -1? Any real number that I can put in for x that'll make it -1? Huh? In other words, x squared equals -1. And we take the square root of both sides. So x equals plus or minus the square root of -1. Is the square root of -1 a real number? Someone tell me.
No.
No. It's an imaginary number. We're going to get to that a little bit later. This actually equals plus or minus I. I is just a symbol that represents the square root of -1. There's no magic here. There's no explanation other than this is a symbol we use for the square root of -1. And this means, the reason we use I is because when they were discussing this, they were talking about the real numbers are the numbers. These numbers, the square root of negative numbers, aren't real. They're imaginary. And the name stuck. Because then we have the real numbers and the imaginary numbers. And when you combine the real numbers with the imaginary numbers, you get the complex. So real numbers and imaginary numbers are subsets of the complex numbers. And this is what we call a pure imaginary number, where other complex numbers are not pure imaginary numbers, because most complex numbers have a real component as well as a negative, as well as an imaginary. So because this will never equal 0, then I can put any number in for x. So that's why the domain here is all real numbers. This is pretty much like the first one we saw. You set x minus 2 equal to 0, and you find out that 2 gives us 0 there. So 2 isn't part of the domain. So it's going to be x is a real number such that x is not 2. Or x does not equal any real number but 2. So to analyze this graph, we look at those components. We look at what happens here, right? What is the domain? Well, the domain is all real numbers but 0. Why not 0? Why not 0? Why can't I have 0?
Because the function no longer is no longer applicable at 0.
What were you saying?
Q cannot be equal to 0 because the function wouldn't exist.
Right. So x can't be 0 because 0 squared is still 0. So we can't have 0 down here. So that's why it's not 0. It's all real numbers except for x equals 0. Right. The graph has no y-intercept because you can't use 0 to find the y-intercept. And 1 over x squared equal to 0 has no solution, no real solution. It doesn't have a solution. Because to find the solution, you multiply both sides by x squared and you get 1 equals 0, which is a false statement. So boom, no solution. Therefore, the graph of h does not cross or touch either of the coordinate axes. So it doesn't touch or cross the x-axis or the y-axis. Putting negative x in for x, we get h back. So what does that tell you? What does that tell you about the function h? You put negative x in for x and you get the function back again. What type of function is it? Just because we covered it and had an exam over it means you can forget it. Still going to be using that. It has a certain type of function that has a certain properties, which we use. So it's an even function. Remember that now? Light bulbs are going on in the head. Okay. So this is an even function. So that means it's going to be symmetric to the y-axis. And so we only needed to select the positive numbers for x because the negative 1/2 will give us 4, and negative 1/100 will give us 10,000. Negative 1/10,000, negative 1/10,000 will give us 100 million. 1 will give us a negative 1 will give us 1. A negative 2 will give us 1/4. A negative 100 will give us a positive 1 over 10,000, and a negative 10,000 will give us 1 over 100 million. Right now, something they want you to notice here is as x gets smaller, the y values get larger. So as the fractions get smaller, as the x approaches 0, the y values become unbounded in the positive direction. In other words, they get more and more positive. They get larger and larger positive numbers. I keep looking at that stupid thing. Okay. So they use this notation: x approaching 0. H of x will approach infinity. And the first thing you cover when you take out calculus 1 is limits. because derivatives are limits, and derivatives are the driving nature of calculus. Thank you, Sir Isaac Newton. Okay. Leibniz looked at calculus going from the other direction. So he did differential calculus. No, he did integral calculus, where Newton did differential calculus. They were looking to answer different questions and came up with the same, different sides of the same point. Anyway, so this notation is read: the limit as x approaches 0 of h of x equals infinity means that the function is going to infinity as x increases without bound. As x approaches 0, the function increases without bound. In a similar manner, as we look at x going to infinity, as x is increasing in value, so we're getting more and more positive, larger positive numbers, the fractions are getting smaller and smaller. They're approaching 0. So as x approaches infinity, that's what's happening here, then the h of x, the function itself, is approaching 0 because these get smaller and smaller fractions. They get so small, in fact, that you can't tell the difference between that number and 0. The micronic microscope to see the difference. And so the graph here are 3 points from the graph. And if I change the sign on the x, that'll give me another point on it because it's symmetric across y, x equals 0. And so 1/2 4, -1/2 4, 1 1, -1 1, 2 1/4, -2 1/4. And so as x approaches 0, the y values explode upwards. And as x goes toward positive and negative infinity, the graph moves down closer and closer to y equals 0. And notice these they put in these dashed lines that you can see it coming out. Those are what we call asymptotes. Because as x approaches infinity, this is the smallest, the function itself is approaching 0. So we're getting closer and closer to 0 here as the x values get more and more positive or more and more negative. The y values get closer and closer to 0. And as x gets closer and closer to 0, the y values keep getting larger and larger. They go towards infinity. And so that, yeah. And I pointed that out because I knew they were going to say it. Now, the graph of this rational function, we can, since we know the graph, what the graph of 1 over x squared looks like, I can use transformations to find the graph of this function. All right, this is 1 over x plus 1 squared minus 2. There's a minus sign. Like, and there's a fraction mark here. Okay. So it's 1 over x plus 1 squared minus 2. Now, I always look to see what happens to my 0, 0. The domain is a set of all real numbers except for x equal to -1. So that means 0, 0 got moved over to -1, 0. So to start with, we start with this graph. And they have x plus 1, but this is a typo. Someone should have put, they should have put a plus here instead of a minus. But the shift here is to the left because what makes x plus 1 equal to 0? Well, that's -1. So that means I'm shifting this over to here. So I'm shifting my vertical dashed line over 1 unit. And so the whole graph got moved to the right, to the left, 1 unit. So that took care of the horizontal shift. Now we have a vertical shift of -2. So that means this whole thing gets moved down 2 units. So instead of 0, 0 being here, now 0, 0 is going to be down here at -2. So it's going to be -1, -2. Which they have over here. So 0, 0 went to the left 1 unit, and then it went down 2 units. So 0, 0 moved from here down to here. And that means these 2 points, the -1, 1, -1, 1 got moved to -2, 1. Which got moved to -2, -1, because we dropped down 2 units. 1, 1 got moved over to 1, 0 to 0, 1, and got moved down 2 units to 0, -1. My x-axis got moved down to -2. My y-axis got moved over to x equals -1. Questions here? You will see this in the homeworks. This type of problem you will not see on an exam. But understanding how these things work helps you see certain things within functions. All right, now we're going to talk about horizontal and vertical asymptotes. All right. So R is a rational function. And as x approaches -infinity, or as x approaches positive, the values of the function approach some number L. And so that's what they're saying here with this. Then the line y equals L is a horizontal asymptote. We use L because it's a limit. As the absolute value of x approaches infinity. No, this is vertical. Horizontal. As x approaches -infinity, the function approaches L. And as x approaches positive infinity, x will approach L. Then the line y equals L is a horizontal asymptote. So it's a horizontal line, y equals L. So that's here. y equals -2 is a horizontal asymptote. Now, as r of x approaches infinity, the absolute value, that means as it approaches negative infinity or approaches positive infinity, then the line x equals c is a vertical asymptote of the graph. So you have a vertical line where on either side of that line, as x approaches that c value, the graph goes to positive or negative infinity, which happens here. As x approaches -1, the graph approaches positive infinity on either side. Now, sometimes it'll approach negative infinity and positive infinity on opposite sides. But that would still make it a vertical asymptote. So these are the situations that can occur, or that do occur. All right. Horizontal asymptotes are all about the end behavior. What happens in between, it can cross a horizontal asymptote. But once x gets sufficiently large enough, it'll never touch that horizontal asymptote again. So it'll only touch it somewhere in here if it touches it at all. Same thing here and here. So here they show it approaching from below, but it could approach from above. So it can come down towards it, like this one's coming down towards it, but it could have been coming from below. And just like with the 1/x², as it approached the c value, both sides went up. Well, or both sides could go down. What if that was a negative 1/x²? So then it would have been going down. But then sometimes you have it like this, where one side is going down and the other side is going up. Or it could have been going up here on this side and down on this side. So those are the situations that can occur. So they can both, for a vertical asymptote, on both sides, it could be both going up or both going down, or they're both going in opposite directions. So you have one of these two happening for vertical asymptotes. And horizontal asymptotes are about in behaviors. And as x gets sufficiently large enough, either in the negative direction or the positive direction, then we're looking at, is it coming down to that line or coming up to that line? And usually it's pretty easy to tell what's going on there. Usually, and we'll look at examples of doing that. Now, locating vertical asymptotes is not too difficult to process. It can get complicated depending upon what the denominator is. Because the function cannot be 0 in the denominator, so I want to set the denominator equal to 0 to find out where x can't be. And that gives us our vertical asymptote. Provided we reduce the fraction. So that means we're going to have to do factoring here. So we're going to look at the function both in the unfactored form and the factored form to determine things about the function. All right, the vertical asymptote here is when the denominator equals 0 in reduced form. All right, this is in reduced form. If I put 3 in for x, I get 0 in the denominator. So x equals 3 is the vertical asymptote. If I set this, if I factor this, I have to factor this first. So I get x minus 7 times x plus 7. Right? I have the difference of two squares. The square root of x is x, the square root of 7, the square root of x squared is x, the square root of 49 is 7, so it's going to be x minus 7 and x plus 7. And I set each of those equal to 0, so I get x equals a negative 7, x equals a positive 7. This function is in reduced form, or in lowest terms. And so x equal to a negative 7, x equal to a positive 7 are the vertical asymptotes. And the horizontal asymptote is y equals 0. And here the horizontal asymptote is 1. And I will discuss how to determine. Here, the denominator will never equal 0. Right? X plus 9 will never be 0. The smallest, the denominator, the smallest number the denominator can be is 9. Right? Because once I get off of 0 and I square it, I'm going to be adding a positive number to 9. So it's going to be greater than 9. So we don't have a vertical asymptote. We do have a horizontal asymptote. That's 1. Now, letter G, we want to factor everything first. And once we factor everything, we can determine what our vertical asymptotes are. So we'll get to that in a second. Because I'm going to look at these. So x equals 3 is the all right. So this is in lowest terms. The only real 0 is the denominator is 3. So the line x equal 3 is the vertical asymptote of the graph. Because we factored x squared minus 49. So that means x equal to negative 7 and x equal to 7 are the vertical asymptotes. You can do that by factoring, or you can do that by using the square root property. X squared minus 49 equals 0 means that x squared equals 49. Taking the square root of both sides, you get plus or minus the square root of 49, which is plus or minus 7, which is negative 7 and positive 7. And then, so this is in lowest terms, and the denominator has no real zeros, so it has no vertical asymptotes. Letter C is not, letter D is not in lowest terms, because we can factor our numerator and factor our denominator, and we have a factor in common. So once we cross those out, because they're 1, that equals 1 here, so they go away, and so here we have it. So that means when x is 7, negative 7, we can't use that in the denominator here. So x equal to negative 7 is the vertical asymptote. Now, an important thing to realize here, positive 7 can be used here. I can use positive 7 here, but I can't use positive 7 over here. Because +7 in here gives us 0. This is the original function. This is not the original function. Okay? This is the original function. So that means I can't use 5 here. Because when I put 5 here, I get 0 down here. So that means even though I could put 5 here, that'll be 10/12. 10 divided by 12 is what? 5/6. When I have 5/6 on the graph at 5, so at 5 over here, it's at 5/6, so I have to have an open dot. All right, the graph will go through that. All right, so at -7 down here in this one. So that means it's going to be coming up from down here, going through there. I think, yeah. So when at 5, we have an open dot on the graph. That's how we show this. That's how we show that it can't be 5. But 5, x = 5 is not a vertical asymptote because on either side, it's approaching that number 5/6. Or is it 5? Yeah, 5/6. But once you get to 5, it's no longer there. Poof, it disappeared. So that would give us an open dot on the graph. You will see those in the homeworks. You will see them in examples that I give you, but you won't see them on the test. So it only has one vertical asymptote, that's -7. And the horizontal asymptote is 1. Because now we're going to talk about finding the horizontal or oblique asymptote of rational functions. Now, the horizontal depends upon the leading terms, the 2 leading terms. And you compare the degrees of the 2 leading terms. If the numerator has a smaller degree than the denominator, n less than m, the degree of the numerator is less than the degree of the denominator, then the line y = 0 is a horizontal asymptote. Right? So, all right, this one. The degree up here is 1. The degree down here is 2. So this degree is less than this degree. So the horizontal asymptote is y = 0. So the x-axis is the horizontal asymptote. Okay. Now, if they're equal, like on a couple of those, it was x squared in the numerator and x squared in the denominator. And I said that the slope was, I mean, the over here, the horizontal asymptote was 1, y = 1. Well, if the degree of the numerator and the degree of the denominator are the same, then the slope, then not the slope, then the horizontal asymptote is y = a fraction of the leading coefficients. Right? The horizontal asymptote equals the ratio of the leading coefficients. So if we bounce back here to this one. Okay. So my leading coefficient here is 1. My leading coefficient here is 1. Those are the same. So it's going to be y equals 1 over 1 or 1. Same thing here. The degrees are the same. The leading coefficients are 1, so it's 1 over 1, same thing. If this was 2x squared, then it would be 1 over 2, which is 1/2. So y equals 1/2. Okay. Now, if the numerator is a larger degree than the denominator, then you don't have a horizontal asymptote. You could have an oblique asymptote. What we mean by oblique, we have an oblique angle. In mathematics, we have right angles, but then we also have oblique angles. And so we're usually referring to the angle it hits the horizontal, the vertical width. And it's not a 90 degrees, so it's not horizontal, it's oblique. So that if the numerator is 1 more than the denominator, so you have x squared in the numerator and x in the denominator, or you have x to the 4th in the numerator and you have x cubed in the denominator. The numerator is 1 more than the denominator. Then after you do division, you will wind up with with the equation for a line plus a remainder. And so that line is the oblique asymptote. Am I going to have you do polynomial division? No. Unless you can do synthetic division, I'm not going to have you do this. So if you have x squared over x, then yes, I will have you do this. I'll give some problems that are that way. I don't know that this all I see it. Never say never. Okay. Now, if n is more than 1 plus, then 1 more than the numerator. So it's 2 or more. Then you won't have a horizontal or an oblique asymptote, but the end behaviors will resemble, not be the same as, but will resemble. If they're both going up, or they're both going down, or going down to the left and up to the right, or up to the left and down to the right, or whatever, is determined by the leading terms, the 2 leading terms, and you subtract the exponents n minus m, so you'll get a positive exponent. And you'll only get a positive exponent there because n will be larger than m. So the smallest exponent you'll get here is x squared. So if this is 3 and this is 1, or if this is 17 and this is 15. So the end behaviors will be like x squared, and they'll both be going up if n over m, if the leading coefficients is positive, or both of them are negative, then they're both going up. But if one of them is negative and the other is positive, then both ends are going to be going down. A rational function will never have both a horizontal and an oblique. It'll either have one or the other or neither. So you can have functions that have neither, they have no horizontal or oblique asymptotes. And they could have a vertical asymptote. Those graphs look kind of weird. Not that any of these graphs look normal. So what I'm going to talk about right now is what we just talked about. So you compare the numerator. You compare the degrees. If n is less than m, if the degree of the numerator is smaller, then it's y equals 0. The horizontal is y equals 0. If the degrees agree, meaning they're the same number, you have a third degree over a third degree, or you have a 12th degree over a 12th degree, then it's y equals the fraction of the leading coefficients. And if n is the larger of the two, you have no horizontal. No horizontal. But then you have to look at, does n equal m plus 1? Then you have oblique. And it will be of the form y equals ax plus b. Or a is the slope. So we could put m here, but they chose to use a. So you have oblique, and if n equals, no, n is greater than m plus 1, or the way they say it is that n is greater than or equal to m plus 2. I like this way because it's pretty clear that it has to be greater than this thing here. Then you have no oblique. So you have no horizontal, no oblique. And the end behaviors, because horizontal and obliques are talking about end behavior. Resemble y equals a sub n over b sub n x to the n minus m. So it'll resemble that. So if n minus m is even, then they're both going to be going up, or both are going to be going down. If n minus n is odd, then they're going to be going in opposite directions. And whether a sub n over b sub n is positive or negative determines whether which is up and which is down. And we're 5 minutes over. So I did not realize I'd gone over. I knew I was getting close. But thank you for staying till I realized I'd gone over time. So, any questions? If you don't have any questions, you are free to go. And I will see you on Wednesday.
See you Wednesday.
Hopefully they'll fix the computers. And I can use the cameras again. Because this sucks. Anyway. I almost used real cuss words in my high school class this morning. Okay, I'm gonna go ahead and end the recording or end the Zoom. And I will see y'all Wednesday.